Welcome back. In this section, we'll be talking about one of the applications of exponential functions, which is financial models, compound interest. When we're talking about money deposited at a bank, we call the amount that we deposit the principal, and we use the letter P to represent that amount. And when we deposit that amount, we're going to receive some money from the bank called interest that they pay us to hold on to their money. Now, the amount that we get for interest is determined by our annual rate of interest, which we use the letter R to represent that. And our interest rate, although we might say it as a whole number amount like 3% or 4%, we always express our interest rate as a decimal. So if we had 3% interest, R would be 0.03. Now, there's two kinds of interest. The first kind, the less interesting kind to us, is simple interest, which that would just be interest based only on the principal. So if you had, let's say, 10% interest and you deposited $100, then every year you would get 10% of $100. Every year the bank would give you $10. So after the first year, you would have $110. And then after the second year, you'd have $120, and so on. That's the reason why I say it's maybe not the most interesting to us, because it's easy enough for us to calculate how much money we'll have at any point, since the interest is always going to be the same amount. Now, the other kind of interest that we're interested in is compound interest, and that's where the bank is not just paying interest on the principal, but they're also paying interest on any of the amounts that we'd deposited previously and any interest amounts we've received previously. So again, if you're imagining we've got $100 and we're getting 10% interest annually, in the first year you would get 10% of that $100, which is $10. So you would have $110 in your account. The next year, the bank will give you 10% of the $110. The bank would give you $11 in interest. You'd now have $121. And then the next year after that, the bank would give you $12.10. You would now have $133.10. You can see that the amount of money that we're going to make each year is going to increase, because not only are we getting a percent of the principal, we're also getting a percent of the interest that we've already earned. So the formula that we have for compound interest takes into account our principal P, takes into account our interest rate R. It also takes into account T, the length of time that we have our money in the account, but also takes into account N, the number of compounding periods per year. How many times per year do we receive interest? So this means that when we're talking about compound interest, there's possibilities of the interest being paid maybe once a year if it's compounded annually, or semi-annually, or quarterly, or monthly, or weekly, or daily. What this means for us is that the amount of interest that we're receiving is going to be sliced into equal-sized pieces. So, for example, if you had 10% interest and you were compounding it semi-annually, that doesn't mean you'll be getting 10% in the first half of the year and also another 10% in the second half of the year. What you'll be getting is 10% divided by 2. You'll be getting 5% in the first half of the year and 5% in the second half of the year to give you 10% in total. So when we look at something like daily compound interest, you might have compound interest where the interest rate is 5%, and if it's compounded daily, then every day you're only getting 1/365th of that 5% of interest. A couple of things just to mention here before we go further. One would be about the business of daily compound interest. There is the very real possibility that you might have a leap year where there's 366 days. For our mathematics that we're doing, we're not going to worry about that. So if it's a leap year or if it's not a leap year, for us, we're not going to care. It will always be 365 days per year. The other thing to note here, one other thing just to mention, I said that R over N, that represented how much interest we're getting at each interest paying period. But we also have the exponent, which is N times T. And that represents how many times you're receiving interest in total. You receive interest N times per year, and you're leaving the money in the account for T years. So N times T, this is how many times in total do you receive interest on the money that you've deposited. So let's do some examples here. We've got $1,000 that we're depositing into an account, and it's paying an annual interest rate of 4% compounded monthly. So some things that we know right away. Number one, our principal is $1,000. We know that our stated interest rate is 4%. It's 4% for the entire year, and it's compounded monthly, so that means we're going to be getting interest 12 times per year. We want to know how much money will be in the account after 5 years. So time here is going to be 5, and we want to know what is the final amount A. We know our formula, A equals P1 plus R over N to the power of NT. And putting in what we have our principal is $1,000. We're receiving 4% interest, compounded monthly. And the power, N times T, 12 times 5, that's 60. That's because over those 5 years, we'll be receiving interest 60 times in total. And then we just have to run this through our calculator. And since this is money, then it makes sense for us to have this in terms of dollars and cents, so 2 decimal places. When I run this through my calculator, I get 1,220.996. So if you're rounding this off to 2 decimal places, that would be 1,221.00. So in 5 years, there will be $1,221.00. All right, now we're continuing on, and the next question is we want to know how many years will it take for my investment to double in value. So in other words, we want our final amount to be $2,000 then, and we want to solve for time. So first off, we have our basic equation, A equals P1 plus R over N to the power of NT. The final amount is 2,000. Our principal is 1,000. What's inside the bracket is still going to be the same. It's still 4% interest compounded monthly. And the thing that's now the unknown is our power, N times T or 12 times T. So now we've got an exponential equation to solve. And we know how to do that from the previous section. First, you would want to isolate that exponential function. So I've divided both sides by 1,000. And this is a word problem, so it makes sense that we're going to want to rewrite this in a way that I can use a calculator to evaluate it. So although it's an exponential function where the base is 1 plus 0.04 divided by 12, I'm not going to use a logarithm with bases 1 plus 0.4 divided by 12. I'll use natural log instead. So I'm going to use that technique where we'll take natural log of both sides of the equation. And we know that when we take natural log of the right side, we'll have natural log of something to the power of 12t. And so that power would be able to come down in front. And so now I just need to solve for t by dividing by 12 and by that natural log. So I can find that t should be equal to natural log of 2 all over 12 times natural log of 1 plus 0.04 over 12. And when I run that through my calculator, I get about 17.357. So I didn't say how many decimal places to give here, so I'll give one decimal place. So 17.4 approximately. And there we go. We have that it'll take about 17.4 years for my balance to double in size. Okay, so now we've got a different scenario here. We have a $500 deposit and we want it to double in value in 5 years. So starting off, we know our principal is 500. We know that in 5 years, when time is 5, we'll have a final amount of $1,000. We want to know what would be the annual interest rate. So the interest rate is our unknown, and it's supposed to be compounded monthly. So this is what we have, and this is what we need to find out. If we have $500, and eventually, after 5 years, it becomes $1,000, what would have been the interest rate? So starting off with our basic formula here, A equals P times 1 plus R over N to the NT, and putting in what we have, so 1,000 equals 500, 1 plus R over 12 to the power of N times T, 12 times 5, that's 60. And same thing that I did in the last problem. First, I'm going to isolate my exponential function by dividing, in this case, dividing by 500. So that'll give me 2. And one thing just to notice here is that I'm not going to have to use logarithms to solve my problem here, because if we're looking at what I have, it's not the exponent that I need to solve for. I need to solve for what's inside those brackets. I know how I can get rid of that power of 60. The opposite of power of 60 would be the 60th root. So if I took the 60th root of both sides, and instead of me writing it as 60th root, I'm going to write it as power of 1/60th. When you take the 60th root of the right side, the power of 60 will be gone. And now you have an equation that'll be easy enough to solve for r. So I'll bring the 1 to the other side. And now I'll multiply both sides by 12. And I can use my calculator to find out that r is about 0.13943. So the interest rate should be 13.94%. So if I want my interest, if it's being compounded monthly, if I want my interest to be enough where my balance will double in 5 years, then I need a much higher interest rate. I need 13.94%. Now, we do have another kind of compound interest where instead of having interest compounded daily or weekly or monthly, where it's being compounded at every instant in time. continuously. So not just every day, but every second, every fraction of a second, interest is being calculated and paid out. One of the nice things about this is that if you were to let n get larger and larger and larger, so if we're thinking back to our compound interest formula, that if you were to let n become infinitely large, as it turns out, this formula becomes equivalent to this. In other words, it becomes equivalent to something involving the natural log's base, which is base e, that natural number. A is equal to p e to the power of RT. That when we look at not just compounding a finite number of times per year, but compounding infinitely often per year, we actually have a different formula for compound interest that involves that special constant e. So this is one place where e emerges in real life. If we're talking about continuously compounded interest, the calculation for that does involve e. This also means that calculations with continuously compounded interest are going to be much nicer for us to do. So, for example, if we're looking at the same problem that we started with, $1,000 at 4%, if the interest is being compounded continuously, so we have a principal of $1,000, we have an interest rate of 4%, and we have the time is 5, we know that A equals P E R T. We have $1,000. E to the power of 0.04 times 5. And 0.04 times 5, that's the same thing as 0.2. So this is 1,000 times e to the 0.2. And if we used our calculators, we'll find it's about 1,221.402. So since it's money, I'll go to 2 decimal places. $1,221.40. Now, just to compare this with our first problem that we did, so notice that here our amount that we would have as our balance after 5 years, $1,221.40. If we were looking at compounding our money monthly only, there's not that much of a difference, $1,221.00. So instead of getting interest only 12 times a year, if we increase it so that interest is happening infinitely often, we're only going to get, at the end of it all, an extra 40 cents over those 5 years. So although it might seem that we're going to get infinite amount of interest if we're going to have interest happening infinitely often, as it turns out, there is a limit to how much interest you can receive. Same sort of question that we had before about looking for our money to balance in size, or balance to double in size. So again, we had our principal, that was our $1,000, and we wanted our final amount to be twice that, so $2,000, and our rate was still 0.04. So A equals P e to the RT, or 2,000 equals 1,000 e to the 0.04 times t. I'll isolate that exponential function by dividing everyone by 1,000. And then I can solve for t by rewriting this as a logarithmic equation, with base e, switching the inputs and the outputs. And then I can find out what t is. It's natural log of 2 divided by 0.04, which, when I run that through my calculator, I get about 17.3286. So it will take approximately 17.33 years for our money to double in size. Now again, comparing that with when we were compounding our interest monthly, first, just to compare with the work that we had to do when we were solving for compounded monthly, it took a lot more work. It was a much more complicated equation, and we came up with 17.4 years. For continually compounded interest, 17.33 years. We've shaved a little bit of time off, but not much. However, nicely enough, this is a much easier equation to solve. All right, let's do one more. I want to have $3,000 in my bank account, so I want my final amount in the bank to be $3,000, and I want this to happen after 6 years. And I want to know how much do I need to deposit now, what's my principal, into an account paying 3% compounded continuously. So let's figure out what our principal needs to be. We know that A is equal to PE to the RT, or 3,000 equals PE to the R times T, 0.03 times T, that's 0.18. And so we can solve and find out that P, our principal, is approximately 2,505.8106 thereabouts. So again, money, 2 decimal places, so I should deposit $2,505.81 now. And if you do that, if you deposit that money now, then in 6 years, you'll have $3,000 in your bank account. Or in other words, you'll have made almost $495 in interest in those 6 years.